Welcome to the second part of this Introduction to Haskell course, and in this video we're going to be learning about types in Haskell and curried functions. We'll now go over the basic types of Haskell that are built into the language, starting with the bool type, which holds logical values either true or false. We then have the int, standing for fixed precision integers. Fixed precision because it has a certain amount of memory dedicated to each value. So it can hold positive and negative whole numbers of a certain range. So from -2 to the power 63 to 2 to the power 63 minus 1. If we use the int type for values outside of this range, it will yield unexpected results. So if we do want to go out of that range, we have the integer type, which is an arbitrary precision integer. And it's the same thing as int. It holds positive and negative whole numbers, but it does not have any memory limits. So we can have a number that's outside of the int range and everything will work fine. But if we know that we will be in range, it's always better to use int because of performance reasons. Next, we have the float type, which stands for single precision floating point numbers. So these are positive and negative decimal numbers. Up to a certain precision, limited by a fixed amount of memory. Precision here refers to the number of digits after the decimal point, so how precise the decimal number is. On the same note, we have double, which stands for double precision floating point numbers, and it's also used for storing decimal numbers, same as float, but it has double the memory assigned for increased precision, so we can have more precise decimal numbers. Now we have chars, which are single characters. This type can hold any Unicode character, and it is enclosed in single quotes. It can also hold control characters, such as /n for new line, or /t for tab stop, and so on. We also have the string type, which stands for a string of characters, so just multiple chars joined together. So simply holds a string of characters. It is enclosed in double quotes, unlike char, which is single quotes. And the type of string is just a list of chars. Now Haskell uses something called the static type check. And this is why it's also called a statically typed language. This means that each expression type is known at compile time. And compile time is important here because it's compile time and not runtime. This is good for us because it adds reliability in the sense that if our program compiles, when we run it, we can be sure that we will not get any type errors. We could get other errors, of course, but type errors we are safe from because of the static type check. This does come at a cost of increased compilation time. And also, as with any compiled language, if we make changes to our programs, we need to recompile them in order to run the new versions. Type signatures in Haskell are signatures of functions that specify argument and result types of those functions explicitly. I say explicitly because if we do have a type signature of a function, then that explicitly states what the function types are. However, it's not always necessary to have a function type signature, because Haskell can still infer expression types even without the signature. However, it is best practice to always write the type signatures So how do we define a type signature for a function? Let's use our triple function example from before. So we have the function definition here as before, and to define a type signature, we would put it just above the function using the same function name, then followed by double colon, which signifies which is the syntax to define a function type signature, and then we have the actual types of the function. So the last type here is always the final result of the function. So we could have multiple types here, but here we have just one. So we could read this as, we could read the full type signature as triple is a function that takes in one argument of type int and then produces a result of type int. So the type signature just specifies the types of its arguments and the type of the result the function produces. So if we define triple like this with a function type signature that explicitly says it takes an int and returns an int, then our function triple can only accept an int as an argument. Any other type will produce an error. So if we try to triple a float, for example, it will result in a type error because the function is defined as taking an int argument only. So here's an example. If we try to apply triple to 3.5, we'll get a somewhat lengthy error message. And error messages in Haskell sometimes are not very intuitive, but this is a simple example, so I guess it's not too hard to understand. It says no instance for fractional int arising from the literal 3.5, and it basically means that we apply the wrong type to the function and it doesn't work. Now we come back to the polymorphism that we mentioned earlier, and the question is, what if we wanted to accept both integer and floats for our function? We want to make the function work with both types. So in that case, we can use polymorphism, which is used for when multiple types can work with the same function, can be used for the same expression, the same argument of a function. And if we redefine our triple function's type signature, such as this, so the same as before, triple double colon, and then we have this thing called num a, and also the equals and right arrow, and only then do we have the actual type signature. So this now reads as, if we read only this part, a to a, this reads as triple is a function that takes a type of a and returns a type of a. And the question is, what is the type of a? So this is what is defined before this equal right arrow. It says num a. So this means that in this type signature, a will stand for a type that is constrained by the num class. So a will be a polymorphic type variable. So the type variable that we talked about earlier is a, lowercase a here, with a class constraint, and this class constraint is num. So we'll get into classes a bit later in the course, but for now it's enough to know that just that num is a class, and both float and integer int are instances of the num class. So this is an example of polymorphism where triple now says the function works with any numeric type, let's say. And if we reload our newly defined triple function and try to use it again with 3.5, it will now work as it accepts any numerical argument, which can be both float or integer. Overloaded types, this is something we just used in the previous example. So an overloaded type is any type with a class constraint. So our triple function became an overloaded function because we used a class constraint for num a. So num is the class constraint and a was the type variable. Any type that uses a class constraint is an overloaded type. But it is also possible to specify a type variable without a class constraint. So instead of using num a, we could just use a. This would, since we are not using a class constraint, would mean that it's not an overloaded type, but instead it's a completely polymorphic type in which any type is valid. There is no constraints, and the type variable stands for any possible type that we have. Now we'll take a look at some data structure types in Haskell, starting with tuples, which are types that can contain elements of different types, and they always have a finite number of elements. To define them, we wrap them in parentheses and separate the elements with a comma. So in this example, we have a string value of Cardano and a Boolean value of true, and therefore the type of this tuple is so parentheses, meaning this is a tuple consisting of a string value and a bool value. So we can see that tuple types depend on both the number of elements in the tuple and the individual types of elements in the tuple. So here are some examples contrasted with the list type. So in the first example, we have a list of 1, and the type of this list is a list of int. So the type of the list is the same regardless of its length, because if we have another list of length 3, 1, 2, 3, the type of this list is still just a list of integers. So it's regardless of the length, it's the same type. However, with tuples, if here we have a tuple of 2 integers, 1 and 2, the type is tuple of int. But if we have a tuple of 3 integers, 1, 2, and 3, then the type of the tuple will also have 3 elements. The type signature of the tuple will also have 3 elements. So the type of the tuple changes with the length of the tuple, or the number of its elements. Now, lists. Lists are sequences of elements of the same type. So unlike tuples, a list can only contain elements of the same type. Elements are wrapped in square brackets. So tuples, parentheses, lists, square brackets. Here we have some examples. So a list of booleans, false, false, true, a list of integers, 1, 3, 5, a list of chars, ABC. Lists can contain other lists, given that all the lists in the first list are of the same type. So in this example, we have an outer list here that is composed of 2 lists of integers, and the type signature here is therefore a list of integers, or a list of lists of integers, better say. Lists can also be empty, so this is an empty list, just empty square brackets. Now let's take a look at how lists are generated exactly in Haskell. So they're always generated from an empty list that we just saw earlier with a constructor called cons. And this is, the constructor is basically a colon, but it's actually a function, so it's wrapped in parentheses here. So when lists are generated, each new element is added to the start of the list. And to better understand this, we can have an example here. We can go through the example of a list generation. So if we define a list as a series of integers 1 through 5, then what this actually means in Haskell is this. Basically, our definition on the left is sort of like syntax sugar for what's on the right, meaning that we could actually write this list 1, 2, 3, 4, 5 in this way with the cons constructor. But of course, we're not going to do that because the one on the left is much easier to write and looks nicer. But it's equivalent to this in any case, where we have basically nested function application of the cons constructor, and the deepest nested function application is this one, 5 cons empty list. So the deepest nested parentheses will be evaluated first, and in this list generation example, this means that we first 5 constructed to the empty list with the cons constructor would be evaluated first. The result of that would be a list that contains just the number 5. Then after that, 4 cons, the result of the previous iteration, would be applied. We would get a list of 4, 5, and the same way further down. So 3, 4, 5, 2, 3, 4, 5, and finally 1, 2, 3, 4, 5. So you can see that each element in this list is added to the beginning. So the cons constructor adds elements to the beginning of the list. Now we'll take a look at some list functions that are useful when working with lists. They are loaded by default in the prelude with the data.list module of Haskell. And the first function we're going to look at is head, which returns the first element of a list. So head applied to a list of 1, 2, 3 will return the first element 1. Also, the tail of the list will return the tail of the list. And so head, as we saw, is the first element, and tail is considered everything except the first element. So take away the first element and return the rest. So in this case, applied to the list of 1, 2, 3, we would get a list of 2, 3 back as the tail of this list. We have the plus function for lists, which join two lists together, so concatenation. And if we join the list of 1, 2, and 3, 4, we get back 1, 2, 3, 4. So here is enumeration, which we already saw in the previous video. So if we have a list and we say, it's basically like saying generate a list of 1, 2, 5 with the double dot syntax, we will get back a list of 1, 2, 3, 4, 5. And we can also use enumeration with a step. So if we define the first elements of the list as 1 and 3, then it's obvious that the step is 2. And if we then use enumeration from 3 to 10, Haskell will use the same step for the rest of the list generation. So we will get 1, 3, then 5, 7, and 9, and we won't actually get 10 because it doesn't match the step. A few more examples here. We can see that enumeration can also work backwards. So we can create a list of 5, 4, 3, 2, 1 using enumeration. It also works with characters, chars. So here we say generate a list from A to Z, and it will generate all the characters between A and Z. This is because characters do have an order like integers. So next up is replicate. And this function is used to create a list by replicating a certain amount of times the second argument of the function. So the first one is the amount of times we want to replicate an argument, and the second is what we are replicating. So in this case, replicate 3 times true, we'll get a list of true, true, true. Then we have the take function, which is used to take the first number of elements of a list from the start of the list. The first argument specifies how many elements we want to take, and the second argument is the list that we want to take from. So here we have take 2 from the list of 1, 2, 3, 4, 5, and we get back the first 2 elements, 1 and 2. Finally, the drop function is similar to take, but reverse. So instead of taking the first two elements, we drop the first two elements. We can also drop arbitrary number of elements. Here in the example, we use 2, so we'll drop the first 2, and we'll return the what's left. So drop 2 from the list of 1, 2, 3, 4, 5. We drop 1 and 2, and the result is 3, 4, 5. Now function types, we basically already went over them with function types signatures, because the type signature of a function specifies the function type. But what I want to mention here is that since functions are expressions, as we saw in the first video, we can use them as any other data type actually. So we can create a list of functions instead of list of just values. Here we have an example of a function list that contains the functions plus and star, which is addition and multiplication. And if we check the type of this list in GHCI, we can use the :T for type. So check the type of this argument. So fun list. We'll get back this num A, and then a list of A to A to A. So we can read this as the type of fun list is a list of functions that each take an argument A and another argument A to give back a final result of type A, where the type of A is constrained by the class num. So any type belonging to the num class is okay for these functions. Besides returning their final result, functions in Haskell can also return other functions. And this brings us to the concept of curried functions. And curried functions take in one argument at a time. So if a function accepts multiple arguments, they will be applied one at a time. And they will return functions that take in the additional arguments. This is actually the default way of how function application works in Haskell. So to illustrate this, we'll take an example of a multiply function that takes in 3 arguments and just multiplies them all together, x times y times z. If we check the type of this function, we'll get 3 arguments and the final result, all of type A, which are constrained by the num class. But what this actually means, what this type signature actually means, is more like this with parentheses. So we take in the argument A, and after that we return a function which is represented by parentheses here. We return a function that takes in another argument A, which returns again a function that takes a final argument A and then finally produces the final result A. So this means that we don't have to apply all 3 arguments to the function at once. We can just apply 1 or 2 of them, and instead of a final result, we'll get back a function that takes in the missing arguments to give the final result. This concept of not applying all of the arguments to the function is called partial application. And so currying enables this concept of partial application, where we call a function with only some of its arguments. We get back a function as a result that takes in the additional arguments. And this enables us to create new functions from existing ones, not by applying all the arguments, but just some of them. So in a silly example that we have here, imagine that from our multiply function that takes in 3 arguments, we want to create a new function multiply by 2 that just multiplies an argument by 2. We can do this with partial application, by specifying that multiply by 2 is the function excuse me, is the function of multiply 1 2. So multiply 1 2 here is the partial application. We apply the first two arguments 1 and 2. So because we want to multiply by 2, we the third argument will be multiply by 1 and multiply by 2, which is equal to multiplying it by 2. And if we check the type of this new multiply by 2 function, we'll see that it takes just one argument and gives back the result. And if we test it out, we can say multiply by 2 and the number 5, and we'll get back 10. So this is a very silly, of course, example of partial application, but this is how it works. So we can take an existing function, apply some of its arguments with partial application to get back another function as the result, and we can use that or to define other functions. That's it for this presentation, where we explored types and curried functions in Haskell. So let's get into the practical part now. This is going to be another short practical session because we're just at the start of learning Haskell and there's not much to practice yet. But in any case, in the presentational part, we talked about types in Haskell and curried functions or partial application. So we'll try to do that now with actual coding. So the first thing we will do is write a type signature for our triple function. And as you can see here, the IDE is offering me some help with writing it automatically. So if I just click this, I'm gonna get a type signature, which is fine. And we saw this one in the presentation. So it uses a class constraint num and a type variable a to define a type signature so that this function works with any numeric type, and that is of class num. Instead, let's just start with what we had at the start also, and we'll just say that triple works with just integers, so it takes an int and gives back an int. If we load this up in GHCI with load triple, we can now use the triple function for 3, but if we try to use it with a floating point number, we get an error because it's not defined that way. So we can change it back to the overloaded type signature, and then if we use :R stands for reload, then we'll reload our already loaded module, and if we use it now, we can work with floating point numbers as well. Now let's take a closer look at the data structure types that we mentioned, lists and tuples. We can start with tuples, and we said they're always defined with parentheses. So this would be an empty tuple, also called a unit in Haskell. But we can have other ones, such as the one we had in the presentation was Cardano and true. So this is a valid tuple, and we can also ask GHCI to give us the type of this tuple, and then we will see that the type is a tuple of a string value and a Boolean value. So in tuples, different elements can have different types. However, in lists, this is not possible. So for example, lists are defined with square brackets, and if we try to have the same values in a list, we will not be able to, because there's an error and we couldn't match the type Boolean with the type char, or a list of chars, which is a string in this case, so Cardano. So this doesn't work, and the only list we can have is where all the elements have the same type. So if we cast true as a string value, then this is okay, and the type of this would be a list of strings, which it is. We also said that lists can contain other, a list can be a list of lists. So this is a singleton list where the only element is an empty list. And here we have a type variable a, which says that the inner list could be composed of anything. It's an empty list. But so let's make a somewhat better example. So if we have a list of lists, and let's say this is some numeric list 1, 2, 3, and then we can have another numeric list here, and this is fine. It's a valid list type, and we can say that this is a list of lists of numbers, because in here the type variable a is constrained by the num class. So this is fine. However, we cannot have a list of lists where the inside lists are made up of different things. So if the second list is made up of some characters or chars, then this does not work, because both the inner lists must be of the same type, and in this case they are not. We also looked at some basic list functions, so we'll explore those now. We saw functions such as take, so like take 2 from this list and it will take the first 2 elements. We saw head, which gets the head of the list. We saw tail, which gets the tail of the list. So head is the first element, tail is all the other elements. We had also list concatenation, so a way to join 2 lists together. If we have a list of 1, 2, and 3, 4, with the plus plus operator, we can join them together using concatenation. So now let's try to define our own function for working with lists, and this function will be a function that accepts 2 arguments, 2 lists, and returns the head of the first list joined with the head of the second list. So we can call this function firsts, and first we want to write the type signature for this function. So since we wanted to work with any type of list, it doesn't matter what type it is it a numeric or a string or whatever, we can just use the completely polymorphic type variable without a class constraint, just a, but we do want it to be a list value. So we want the first argument to be a list of a's. The second argument also needs to be a list of a's, because we will be joining them together. So we can only join 2 values together in a list if they are of the same type. And the final result will also be a list of a's. So the second line will be the implementation. And so how do we do that? So we take a list of a's, we take another list of a's, and we need to give back a list of a's. So we can check the type of our head function, and we know that it accepts a list of a's and returns an a, the first element a of that list. So we cannot do just concatenation with plus plus, because we can also check the type of plus plus. Sorry, we have to wrap it in parentheses, because to signify that we mean the function, because plus plus takes a list and another list and adds them together. But since we're going to be using the head function, because we just want the first elements, we will not have the list of a. So we can even have a simpler approach without the plus plus operator. So we can just define our new list here, and we can say this. We know that this list will be composed of 2 elements, the first one from the first list and the first one from the second list. So the first element is going to be the head. Oh, and we need to put the arguments here. The argument name for a list is usually followed by s. This is standard. So instead of just calling the argument x, since it's a list, we will call it xs, and the second list will be called ys. And now the first element of our result list will be the head of xs, and we can just use comma, and the second element will be the head of ys. And that's it. this should work fine. So if we reload our module, we can see that it compiles correctly. And now if we take firsts and apply it to two lists, let's say 1, 2, and 3, 4, we will get back the list of 1 and 3, which is the first element and the first element of the first list and the first element of the second list. Now that we have this function which accepts two arguments, we can also check curried functions and partial application with this function. So we can do something like this. Firsts applied to 1 and 2. We will get an error because it did say, have you applied enough arguments to this function? Because it's trying to evaluate the full function here in GHCI. But we can say something like firsts, and we'll just use a prime here. And firsts prime equals to firsts 1, 2, and this is fine. So now we used partial application here. We applied it to just one argument. Well, actually we defined another function that uses partial application of this first function. And we can now check the type of firsts prime. And we will see that instead of, as the first function accepts two list arguments of type A, firsts accepts now just one of type A, and now type A is automatically constrained by the num class because the list that we applied here is 1, 2. We could, instead of 1, 2, use some characters. And then if we check this first prime type again, we'll see that it's a function that accepts a list of characters and it returns a list of characters. So now we can apply this first prime function to another list, say ty, and we get back ct. So the c is the first argument, the first element of the first list that we used in partial application, and then t is the first element of the second list that we used in the final application that completes the function. Also, I just noticed that we defined the first function here and we loaded the module and used it successfully in GHCI. However, we have a module interface that does not export it. It only exports the triple function. So in GHCI, everything from the module will be loaded regardless of the module interface. But what I meant when I said about module interface explicitly exporting things, let's create a new module here, just call it test, and we want to import the functions from our triple module into this one. So module test, where, and to import a module we say import triple in this case, and we can just say, for example, the firsts t function is going to be equal to triple the module times dot firsts. Okay, so already here we have not in scope, the module triple does not export firsts, and if we try to load it in GHCI, this test module, we'll get the same error. So module triple does not export firsts. However, the triple function is exported and it's already offered here. So we can use the triple function fine in the test module. Okay, so this is what I meant by the module interface. If only triple is exported, only triple will be able to be imported in other modules. However, it seems in GHCI everything is loaded regardless of the interface. So that's it for this session. Thank you for watching, and I'll see you in the next video.